Today in class, we worked on task 8.4, comparing methods, a practice understanding task. We discussed different methods for solving equations along with the zero product property, and students had an opportunity to practice factoring, which was developed using the area model in tasks 8.1 through 8.3. In the Ready section, you're being asked to rewrite the quadratic expressions in factored form, which means that we are going to write them as the product of two linear factors. We're starting with 6x squares, and in the area model, you can see that's represented with the 6 squares that are x units long. We're taking away 24 x's from that current area of 6x squared. The red indicates the 24 x's that we're taking away. That leaves us with the dimensions of our full area model, which have a length of 6 x's and a width of x minus 4. Another way to think about this is that the 6x is the greatest common factor of the two original terms. So we're factoring out a 6x from the 6x squared, as well as factoring out a 6x from the 24x. That leaves us with the expression 6x times the difference of x and 4. In the next example, we're starting with a trinomial, and again, we're looking for the linear factors that make up that trinomial. We know that the first terms in each of the factors must have a product that equals the first term in our trinomial. In this case, it would be x times x, which would equal x squared. We know that the last two terms in our factors have to have a product of the last term in our trinomial, which is -8. We start by listing the factors of -8. While we know we're looking for a product of -8, we also know that the sum of the products of our first and last term in our linear factors must equal the second term of our trinomial. In other words, when I multiply the first term of my first linear factor times the last term in my second linear factor and add that product to the product of the first term in the second factor and the last term in the first factor, that sum has to be 2x. You can see that if I place the 4 in the first linear factor and the -2 in the second linear factor, the sum of their products will equal +2. And here's the representation using the area model. In the task today, we looked at solving equations using the traditional inverse operations method versus factoring and solving. Here's an example of what we did in class today. So we're starting with the same equations. On the left, we're showing the process for the traditional inverse operations method. The first step is to add 49 to both sides. We're left with 49 equals x squared. Then we're going to take the square root of both sides, and we're left with x equals ±7. On the right side, we're looking at the factoring method. For the factoring method, again, we're looking for two linear factors whose product will equal x squared minus 49. And we are left with x plus 7 times x minus 7. We're going to set each of those equal to 0 because we're looking for the value of x. And we find that on the left side we have x equals negative 7, and on the right we have x equals positive 7, which are the exact same answers. So in this situation, with this equation, we could use either method, either the traditional inverse operations method or the factoring method. In the next example, we're going to start by taking the greatest common factor of each term, which is x, and setting that outside the parentheses as the first factor. What we're left with is x minus 4. So the two factors are x times x minus 4. We're setting each factor equal to 0 again. On the left, we have x equals 0. On the right, we have x minus 4 equals 0. And for the right equation, we're going to use inverse operations in order to solve for x by adding 4 to each side. So our solutions are x equals 0 and x equals 4. In the last example, we had the expression x squared minus 4x, but it was set equal to 0. In this example, we have that same expression of x squared minus 4x, but now it's being set equal to 12. So the very first step is to get the expression equal to 0. We're going to use inverse operations in order to get the left side of the equation equal to 0. When we do that, we're left with the equation 0 equals x squared minus 4x minus 12. From here, we're going to look for our linear factors. Again, the first terms in each of our factors must have a product that's equal to the first term in our trinomial. The last two terms must have a product that's equal to the last term in the trinomial. So negative 6 times positive 2 gives me the negative 12. And the sum of the first and the last, the sum of the product of the first and the last term in each of the factors has to equal negative 4x. Once we take the x minus 6 and the x plus 12 and set them equal to 0, we solve for x in each one using inverse operations, and we're left with the solution x plus 6 and x equals positive 6 and x equals negative 2. In the next example, we have a binomial that's squared, which, just like any other power, that it just means that that is our the base is our factor, so we have x minus 2, and we're multiplying that times itself. So we have x minus 2 times x minus 2. We're setting each factor equal to 0 and using inverse operations to find the values of x. Notice that for each of these, we end up with a solution of x equals 2. We wouldn't list that twice, because if we were to graph that, it would be located in the exact same location on our graph. So one point would be right over top of the other one, so it's only necessary to write that one time. There's only one solution in this case. In our last example for the set portion, we have a trinomial that's set equal to 0. Again, we're looking for those linear factors that have a product of x squared plus x plus 3. We know that the first terms must have a product that's equal to the first term in our trinomial, which is x times x and x squared. We know that the last terms in our linear factors must have a product that's equal to the last term in our trinomial. In this case, it's 3. So we're looking for the factors of 3. We have 3 times 1 and negative 3 times negative 1. We know already that we can't use the negatives because we need the sum of the products of our first and last terms to equal negative 1x. So when we multiply the first times the last term and add that to the product of the other first and last term, we need that to be a positive 1. And if we use the negatives, we would be adding negative 3 to negative 1, which would be negative 4, not positive 1. So our only option really would be the positives. But in this case, we can see that when we multiply the first term in the first factor, which is x, times the last term in the second factor, which is 1, we get 1x. And when we multiply the first term in the second factor by the second term in the first factor, we get 3x. When we add 3x to 1x, we get 4x. We don't get 1x. So in this case, this trinomial is not factorable. In other words, there are no solutions for this equation. In the Go section, we're finding the X-intercepts. These are the ordered pairs that represent where the function crosses the x-axis. We know that the y values for all x-intercepts must be 0. In this first example, we're starting with a function that's already in factored form, and the two linear factors, x minus 5 and x minus 9, are each going to be set equal to 0, using that zero product property. We know that y has to equal 0 for all x-intercepts because the points are located on the x-axis where our y value is 0. The zero product property states that if any of the factors are 0, then the product is going to be 0. So we know that in this example, we have 3 factors. We have negative 1, we have x minus 5, and we have x minus 9. We know that negative 1 is not equal to 0, which means that either one or both of the last two factors, x minus 5 and x minus 9, must equal 0. Because of this, we can set them both equal to 0 and solve for the value of x. So that's what we do, and using inverse operations, we find the values of x and 9. If you replace the x's in the original equation with the 5 and the 9, you'll see that each of those two factors equals 0. And the ordered pairs, which represent our x-intercepts, are 5, 0, and 9, 0. You can also take note that those factors, the linear factors from the original equation, x minus 5 and x minus 9, are the negative 5 and the negative 9 are the opposites of what our x-intercept values are, our x values for our x-intercepts. So in the linear factor x minus 5, we have a negative 5, and in the x-intercept for that factor, we have a positive 5. For the factor x minus 9, we have a negative 9, and for its x-intercept, we have a positive 9. And in the final example, again, we have a quadratic that's already in factored form, and what's different about this example is that we have a coefficient with the x that's other than 1. Again, we're going to use that zero product property and set each of those last two factors equal to 0. Using inverse operations, we're going to solve for x. In the first example, or the first factor, we're going to subtract 3 from both sides of the equation. We're left with negative 3 equals 2x, and then we're going to divide both sides by 2. And we're left with negative 3/2 equals x. Notice the numerator is the second term in that linear factor from the original equation, and the denominator is the coefficient to the x in that original linear factor. Also notice that, like the last example, it's the opposite sign of the second term. That ordered pair for the x-intercept would be -3/2, 0. That's where the function would cross the x-axis. In the second or the third factor of the equation, or the second linear factor, we started with 4x minus 9 equals 0. We're using inverse operations to add 9 to both sides. We're left with 4x equals 9. And we're going to divide both sides by 4 to get the value of x, which is 9/4. Again, the numerator is that second term, the 9, and the denominator is the coefficient to the first term. Again, notice that the sign is the opposite of the second term in that original linear factor. That ordered pair for the x-intercept would be 9/4, 0. That's the second location where the function crosses the x-axis.